Okay, kids, here we go. Let's talk a little bit about heat of fusion, not heat of confusion. Okay, that's different. Heat of fusion and heat of vaporization. We all know that fusion is just a fancy name for the word melt. Yeah, yeah, we're going to do a lab on the heat of fusion. And you might say, oh, wow, sweet, heat of fusion. That means we're going to study the sun because that's a fusion reaction, right? You get a hydrogen and a hydrogen forming a helium. They fuse together. I can't wait. It's going to be awesome. We're going to take a trip to the sun. Okay, no. Don't take a trip to the sun. It'll be bad for you. Like a trip to Pluto could be bad for you. You ever seen the Magic School Bus? There was an episode in the Magic School Bus where Arnold died. Yeah, he went to Pluto, took his helmet off, dead. Magic School Bus, kid show, but dead. Arnold dead. Yeah, look it up. Okay, scary, sad, okay. Where was I? Oh, yeah, heat of fusion. So the fusion is a fancy word for the word melt. So it means heat of melting or heat to melt. Heat of vaporization means, well, heat to vaporize something. What are you talking about? What are you talking about? Well, let's say you've got a block of ice. Nice little block of ice there. And you want this ice to melt. So the ice, well, what temperature does ice melt at? Okay, you know, 32 degrees Fahrenheit, correct, but let's talk in terms of Celsius. So 0 Celsius, you know that. What temperature does water freeze at? You know, 0 Celsius. Did you ever think about that before? Sometimes people don't think about that. Maybe you just never made the connection that it freezes and melts at the same temperature, at 0 degrees. Freezing at 0, melting at 0. Oh, that's confusing. How can it do both? It depends, okay? It depends. Like those, that underwear that I have to wear now because I'm old. It depends. It's funny. Okay. I love them, though. I don't have to worry about anything. TMI, okay? Too much information. But it depends on which way the heat is flowing. Is heat flowing into the system at 0 degrees? Well, if he's flowing in, you're going to have ice melting. If heat is coming out of the system, you're going to have water freezing. So it depends on the direction of heat flow at that time. What's the environment like? Is it colder outside or warmer outside? Okay, but it happens at 0 degrees. Okay, now that's the heat of fusion temperature for water. You know the heat of vaporization for water. That means when water vaporizes. Okay, what temperature does water boil at? You know, 0, I'm going to say 0. 100 degrees Celsius at sea level. Okay, 100 degrees. So we know that. Now, the heat that it takes to do that is called fusion or vaporization. Now, for water, and this is just water, okay, every substance has its own heat to melt it, has its own heat to boil it or to vaporize it. So for water, okay, now, of course, you could always look these up. Where's my eraser thingy? You can always look them up, but I'm here for you. I want you to sit back and relax. You've had a rough day. Okay, you've had a rough day, so you relax, just watch. So the heat of fusion, HF, sometimes you'll see it though as LF, and that means the latent heat of fusion. It's the same thing. You see it sometimes written this way, sometimes this way. I like using the HF, heat of fusion. A little bit more straightforward. For water, for H2O, is 333. Easy number to remember. Just think 1/2 evil. 1/2 evil. You get it, right? Because you double that, you go 666 evil. Okay? Yeah. 1/2 evil. Easy. So 333 joules per gram. But remember, in physics, we like to use kilograms. In chemistry, it's okay. Joules per gram. Leave it at that. Whatever. But we like using joules per kilogram. So for joules per kilogram, 0, 0, 0. You'll have to tag on 3 more zeros to make it joules per kilogram. Okay, that's the heat of fusion for water. We'll come back to that in just a second. What does that actually mean? And then the heat of vaporization. My blue is dying here. I'll make one more number here. My blue is about dead. Dead blue. Heat of vaporization, sometimes called L sub V for latent heat of vaporization, but I like using the HV. And that's for water, is 2,260. Now, that's its joules per gram, so let's get in joules per kilogram. 0, 0, 0. Whoa, that's a big number. Yeah, that's bigger. Okay, that's bigger than it is to melt. So it's harder to get water to vaporize. It takes more energy than it does to melt it. We'll talk about that in just a second here. Now, any physics book or even chemistry book, they'll have tables for different heats of fusion, heats of vaporization for different substances. So, I've got a table open here in this book here. And I'll just show you this here. Lift up, don't lose the papers. So we've got this table here, and hang on. Show you this table. If you can see on there, okay, heats of fusion, heats of vaporization. Now for water, water has the highest on that table for the heat of fusion. And it's very high. Now, I mean, not quite the highest, but one of the highest for the heat of vaporization. Now, let's talk about why that is. Why is water, so much energy to get it to melt? Now, that doesn't mean that the temperature it melts at. I'm not saying that the temperature that water melts at is higher than the temperature that lead or aluminum melts at. No, that's crazy talk. We're not talking about the temperature at which. We're talking about the amount of heat it takes once you've got it to the temperature, once you've got water, or you've got lead, or you've got aluminum to its melting point. Okay, once you've got it there, and it's going to be higher for lead and aluminum. They melt at a higher temperature. Once you've got it to that temperature, how much heat does it now take to melt it? Okay, now water takes a lot. Why? Because water, and we all remember some chemistry that we did, that water, good old H2O molecule, all right, there's your H2O. It's got these little dot things loosely held valence electrons. I know some of you are beginning to shake, don't stop it. No, chemistry, no. Oh, sorry, but well, be quick, it'll be quick. So here's a water molecule, and the bond in a water molecule is covalent. That's a nice strong bond. So we have another, let's say we got another water molecule over here. Okay, hanging out here. Well, let's draw it like this. No, I want to move this. Okay, let's do it this. So let's do this. Another water molecule here. Okay, another water molecule. Now, this water molecule is attracted to this water molecule. They're both polar molecules. That means they have a positive and a negative side to them. And positive and negative opposites attract. It's a natural fact. Paula Abdul, early 90s, we all remember the song. It's a great song and video. The opposites will attract each other and they'll stick together. Water sticks to itself very nicely, very readily. You know that if you've ever tried diving into a pool with your belly flop, Geronimo! Ow, that hurts. The water molecules like to stick together. They don't want you going through it, so they resist you. And yeah, if you want to break the surface tension, you break a surface tension by going in like this or going in feet first. Otherwise, it makes like a rental car company. It makes like a rental car company. It hurts. Hurts. Oh, bum. So what happens, though, is water is it forms a hydrogen bond. There's actually an attraction between this hydrogen that's positive and this oxygen here that's negative, and that hydrogen bond is a strong, it's the strongest, not the one of, it's the strongest intermolecular force. So something that has hydrogen bonding, okay, the molecules want to stick together. Water has that. Water, whether it's in its crystallized form, okay, there's 6 of those water molecules surrounded with hydrogen bonding. They want to stick together. They don't want to separate. So if you're going to make them melt, no, you're going to have to pump a lot of heat energy in. Hence the high number. Now, if you want to vaporize water, that means you're forcing one water molecule and another water molecule to actually separate from each other completely. Okay, watch water boil. It's good, clean family fun. Fun for the whole family. Gather around, boil some water, and watch the fun. And listen very carefully, because if you listen to water, you can hear the voices. I hear voices, okay? I do. Oh, yeah, so can you. Listen, water's boiling. What happens is this molecule and this molecule here are getting pumped full of energy, and so they start to vibrate very readily. Remember, kinetic energy, more kinetic energy, the hotter things are, the more they move. They start to vibrate so much that that bond, that hydrogen intermolecular bond, will break. They don't want to, but you pump enough in, they'll do it. And you can listen to the screaming. No, baby, no, come back, Shane, come back. Good Western, great Western, look it up. Yeah, you'll hear the screaming. No, you hear the screaming, Clarice, at night, the silence of the lambs. Okay, another great movie, Silence of the Lambs. Clarice, okay, weirdo. Not Clarice, she wasn't, the other guy was. So anyways, the water molecules, no, they separate apart. But it takes a lot of energy to do that. Now, when you're melting ice, you're causing the molecules to rearrange. Okay, they resist doing that, but at least they're still stuck together in the water form. So solid, I don't want to separate from you. I like you. I like you too. We'll stick together forever. Ah, this guy's pumping some energy into us. Oh no. Oh no. Oh, we're water now. Well, at least we're together. We're still together. Hey, it's getting hot in here. What's going on? It's getting hot in here. Hey, he's pumping energy into it. Oh no. That takes a lot more energy. Hence, those two numbers. This is about 7 times greater than this. So you can get the water to break its crystalline structure. It still takes a lot of energy, but if you want it to separate, you gotta pump a lot of energy. Water boils at a very high temperature. For a liquid, that's a high temperature for liquid. Other liquids will vaporize at much lower temperatures. Take some rubbing alcohol and boil that. No, don't do that. Actually, don't do that. Bad things can happen if you boil the alcohol. But it'll boil at a much lower temperature. It doesn't have that nice, strong hydrogen bond that the water has. Okay, so that's why we have such high numbers for water and why we have a much higher number for the boiling or the vaporizing of water than the melting of water. All right, let's see. Heat of vaporization, heat of fusion. Of course, different substances would have different numbers. That's for water only. Okay, we're going to keep this video relatively short. I mean, right, it's like 11 minutes. You say that's short? All right, we're going to do a problem with it when we come back right after this. Take a commercial break.